So I'm going to talk to you as briefly as possible about some ideas of what might be happening in the interior of Enceladus. So you guys have an ideation factory where you're actually going to get there. But I've spent quite a lot of the last decade or so trying to work out how I would work out what we should expect there and how to make the best of what we have previously been able to do, all the kinds of state-of-the-art technologies that we currently have. So Enceladus has become a now I need to work out the slide view. There we go. So Enceladus has become a place of interest since the Cassini mission. And that started really with about 2005 when Cassini first arrived at Enceladus and saw jets of plume material ejected from the South Pole. You know who I am. We talked about Enceladus. So we have stuff squirting out the South Pole of Enceladus. And then on the bottom left is this paper by Southworth et al., where the purple blobs, the purple shading kind of shows you where there's a snowfall map of what's landing on the outside of Enceladus. And the white dots kind of show you where the individual jet points are meant to be coming from or have been inferred from. So this is looking at Enceladus from above its South Pole. And so that's why people have been thinking about the current mission that's been recommended from the Decadal Survey, which is to actually go and do multiple orbits through those plumes, work out where an optimal, basically analyze the surface of the planet, the moon, and then choose a place to land so you could actually collect freshly falling snow from Enceladus, with the anticipation that somehow you can actually infer from that what the ocean inside must be like. So one of the things I've been worrying about is there are complications with that, and they're kind of illustrated in two parts here. The expanded box is the fact that we don't really know what happens to seawater when you evacuate it out into space. And you can't really set up that experiment in an analog field setting on Earth. And so one of the people I'm collaborating with a big consortium project I'm leading at the moment, is Mark Neveu, and he's been actually trying to work out how would you actually do that in a laboratory? How would you actually set things up so that you could take some seawater that's dosed with organic molecules of the kind you might want to look for in a search for life. He's been starting with amino acids, and then seeing what happens when you suddenly evacuate that into a vacuum that's held at very low temperature to try and simulate what might actually happen to any of those organic molecules and whether they would survive. And then the second part is the lower half of that left diagram, which is what actually happens to any water as it's working its way up through the ice shell, that even water that's leaving from the top of the ocean then has to go through some distance of some kilometers to actually get up through the ice and out. And again, that's not something you can simulate easily in the field, at least in the vertical dimension. But another one of my collaborators, Melissa Diaz at Ohio State, came up with the very elegant idea of what if you turn the problem on its side? And so she's got this idea that for the Juneau ice field in Alaska, there's actually a series of transient melt lakes that are uphill from one another, and they drain through aquifers that are basically underground aquifers through ice. So it's basically channels of liquid water passing through ice that actually migrate downstream over exactly the same kind of length scale has been inferred for Enceladus. So that's another part of the project we've got, is that they're going to be going and using bottom penetrating radar to work out exactly where that channel is, and then looking at whether or not there's any chemical fractionation between the ice and the ocean as water, or sorry, ice and water, as water migrates in a direction that we know. So it's a unidirectional flow, just like we expect is happening underneath the ice shell of Enceladus. And then we can see to what extent anything latches onto the wall, to what extent some things are preferentially released back off the wall into the water. So these are all things that complicate the kinds of missions we can imagine at the moment, because we just don't know what those processes will be. And so we don't really know how we can relate what we measure on the outside of Enceladus back to what's going on in the ocean. We can imagine it and we can try hard, but there's really nothing quite like what you guys are discussing, which is let's work out how we get back into this ocean. So the question then becomes, well, where are the kinds of technologies for this? This slide is just from a position piece that Kevin Hand and I wrote some years back now in Nature's Geoscience, which is kind of shows how long we've been thinking about it without necessarily making all the progress you would want. Happily, if you've got friends who are animators who you can get excited about this, and Kevin is big friends with James Cameron, then you can get little movies made about what might happen in the future. Um, so at the time that this got made, which is some years back now, this was entirely science fiction. But there's now been 2 rounds of technology investment from NASA to actually start thinking about how you would build cryobots like this that could melt down through an ice shell on a timescale of a year or two. And that little thread coming out the back is actually where I've been involved. So I think there have been 4 teams in parallel coming up with what the mission architectures might be for the actual vehicle that would get into the water and get into the top of the ocean. And then I've been part of a program that instead just worried about, well, how would you communicate back from the bottom of the ocean, or sorry, from the top of the ocean back up through the ice shell? And that's where that single optical fiber comes in, because that's actually something that I've been using for under ice robotic studies on Earth. But the question would be, okay, so you just drilled through the ice and you got into the ocean. What are you going to do next? So my first idea is, if you think about this little blob at the top of the ocean here, is to think about it as, what's it like if you could drop a bucket down a well? The first bucket of water you can get out is already going to be really powerful. And one of the premises that we've been working on from an oceanography perspective is that in an ocean, it's great to get what the dissolved salts might be. For example, if you can find out that the ocean has magnesium sulfate in it, that might be consistent with a chondritic interior. Whereas if you have a lot of sodium and sodium chloride in particular in your seawater, that would actually be a really good clue that the interior of the planet has differentiated. So it's whether it's got 2 different layers in its rocky interior or whether it's all just one giant blob. I think the current thinking on in Enceladus is that it's all just one current giant blob of stuff that's a frozen together mush of mashup of ice crystals and lumps of meteorite. And that's kind of our ideal from a geochemical perspective, because that's the kind of conditions you need to get abiotic organic synthesis and actually start building some of the stuff that life could live from. But in the first instance of just getting some stuff up and not just looking at the dissolved stuff, but looking at the particulate material could be really powerful, because on the right is some work that Brandy Toner and her group have been pioneering for more than a decade now, which is actually looking at marine particles in excruciating detail and showing that a particle is actually made up of lots of different things. There's an awful lot of forensic information available in a particle. And so that's what we're trying to express here, is that these blobs, which have a dark core and then white and pink things on the outside, is the idea that any particle in Earth's ocean can often have a mineral component that actually is where things nucleate. But you can get organic material in a completely abiotic system. If there's dissolved organics present, which there should be, because there's a lot of dissolved organic material in chondrites, then they would tend to absorb onto those particles. They won't just leave fresh mineral surfaces in contact with the seawater. But then if you've also got minerals and water in contact with each other and they're out of chemical equilibrium and there's organic material accreted there, these may also make little niches, little microhabitats for life. We do find that in marine particles, it's a well-known term that you can actually get little like microcosms, which are out of equilibrium with the rest of the ocean that they're settling through or floating around in. So that would be a first thing to think about, is what can you learn just from the first bucket of water before you think about going anywhere else? But the reason I got into this stuff is on the left is what NASA were presenting as the state of the art for underwater technology about the year 2000. I think this is when I first started reading their things and thought, this is where I thought I know a bit more about ocean technology than that looks like. Maybe there's a role for oceanographers here. And it took 15 years and a change of continent, but here I am. So on the right-hand side is actually as far as we've got to just now, which is, as you can see from the humans next to it, way too big to fit on a spacecraft, but it's at least a prototype which allows us to try and start developing the vocabulary of what kinds of science capabilities do you need to have. So the next thing I want to explain is that even if there is hydrothermal activity at the seafloor of Enceladus, that isn't necessarily the next place you should look once you've got your first bucket of seawater. It could well be that the chemical reactions happening at the bottom are loading up an ocean full of reductants. but that where they can actually meet any oxidants may actually be at the ice-ocean interface. So maybe that's going to be a place that's a really good redox boundary. So that might be somewhere you want to go and visit. So here's the neat thing about the vehicle we've built. It's streamlined so it can actually get through the ocean, but then it can actually open its doors when you get somewhere interesting and do some sampling. And just to give you an idea of, this is kind of illustrative of a point. In this case, this is the view from that robot when you first start searching underneath the ice in the Arctic. And what I want to draw your attention to there are the black blobs. Now, in this case, it's actually light penetrating through the ice where the ice is thinnest that is providing the essential missing nutrient. So when you can actually get light or enough light coming through, then you can start get algae growing on the underside of the ice. And so that forms the basis of a food chain. So I'm not telling you that Enceladus would have photosynthesis because the ice is way too thick, but the concept is if there's one thing that's essential for life and you can only get it at the interface, or if that's the place where it first arrives, then that can actually make for being a biological hotspot and something worth looking at. Although the other thing I hope you picked up on there is that the underside of the ice is not a flat and smooth thing, even when the outside is flat and smooth. The underside can have quite a bit of complicated topography going on. So, but those are things to think about if you actually, like, once you got into an ocean, if you wanted to move around, then moving around at the ice-ocean interface could be a really good plan. Another thing about that topography and another reason why you might want to move around is that on Enceladus in particular, Wan-Ying Kang has been leading a lot of work from MIT, which is all about how, because we know about there being an irregularity in topography at Enceladus, we know the ice is thinner at the pole. That actually requires an awful lot of other things to happen in terms of ocean circulation. It kind of dictates exactly how the ocean is circulating. And specifically, what it means is that because you're going to have ice tending to be melting where it's thinnest and freezing where it's deepest under high pressure, there's going to be both flow of heat, but also flow of water as well, and also flow of salt. So you're going to have more and less saline stuff. And so what is going to happen, and we don't know to what extent, is that this, where you see this O1 symbol, is that there will be layers of different density water underneath the south pole of Enceladus, or any ocean that's set up like that, where there's ice thickness. Wherever the ice is thinnest, you will have fresher water and then increasingly salty layers down. We don't know how strong that effect is going to be, but if it's really bad, what it actually means is that if anything is happening in the bottom of the ocean and coming up towards the surface, or if anything's happening along the ice-ocean interface along the deep parts, that water may not actually be able to make it through this density gradient. It's not definite that that's the case. It's just, it's a thing, it's another thing to worry about, or it's a thing to be aware of, which means even if you got through the hole at the shallowest point and looked around on the underside here, that doesn't necessarily mean that because you've got a sample from here, that represents everything that's happening in the ocean. That may just be representing what's happening, or it might be skewed towards representing what's happening in that little patch of the water that's trapped underneath the thin ice. So another thing you might want to think about then is, or a reason why you wouldn't need to get into the ocean would be to think about, well, what's the ocean circulation pattern going to be like? What's going to be happening with deep ocean currents? What's the density stratification going to be like from top to bottom? How much does it vary? And to show you why this is important, this is another paper from the MIT group. On the left is a model thinking about what's the length scale at the bottom of the ocean, where any buoyancy flux might come from if there's a hydrothermal vent. The height is the thickness of the ocean, and then that omega is how fast is that planet spinning. So for Europa, it's perfectly plausible that you can get a hydrothermal system of the kind we think Europa could sustain, and its circulation would drive a plume all the way up to the surface. So that's kind of cool. If you've got any hydrothermal input at the bottom of Europa, you might think that it would show up at the top of Europa. But you're thinking about Enceladus, so I have to say some bad news. That the way Enceladus rotates, that the same like-for-like comparison suggests that in fact the plume might never actually make it up to the top of the ocean. It could take some thousands of years to get there. So again, if you've got a slow circulation pattern, all well and good if you want to actually have just delivery of chemicals to the top of the ocean and you can wait a couple of thousand years, that's not a problem. But if you really want your life to be forming at the bottom, and that's where the habitable space is, and you want to look for it, you're probably going to have to go down to the bottom of the ocean to look for it and not wait for it to come to you, because who knows who knows what's going to happen to those signals over the couple of thousand years you might be waiting to see them. So the good news is you can actually get to the bottom of an ice-covered ocean and you can get hydrothermal vents. These are ones we saw in 2023 and sampled. And what I want to draw your attention to is not this black smoker, but if you look closely, you can just see some shimmering and Schlieren effects coming out from a different chimney there. Let me just play that back. Now I've pointed out to you where I wanted you to be looking. So it's just in this region here. I apologize if it doesn't show up on Zoom, but the idea is that if you want to go find life anywhere, you wouldn't go and look at a black smoker because it's a 350 degrees Celsius acid fire hydrant. So it's not conducive to life. Life on Earth can make it up to about 127 degrees Celsius, but not much hotter. But the good news is, in the periphery of these things, you can actually get lower temperature flow, where we have actually demonstrated in places like this. This vent in the Arctic is the highest hydrogen concentration we found anywhere at a vent site on the seafloor. And the low temperature fluids right next to it are also hydrogen rich, but they're within the temperature range for life. They're also in exactly the sweet spot for where you might get abiotic organic reduction of carbon dioxide to form small organic molecules. And another reason that that can be encouraging is that Andy Fisher at the UC Santa Cruz has been leading some work recently, which has actually been looking at taking what he's been doing from a lifetime study of hydrogeology in the ocean crust of the Northeast Pacific, and then working out to what extent everything he knows about that works at Earth gravity would actually continue to work under the gravity strengths of Europa in the middle and then Enceladus at the top. So we're going to 10% and 1% of Earth's gravity. And the really good news is that you basically can't stop water flowing through the ocean crust on any of these planets. Doesn't matter what the gravity is. But what actually does happen is that as you reduce gravity, you reduce the buoyancy. So as you warm any water up, it doesn't become as buoyant as quickly, which means it flows more sluggishly. So if you think of like the subsea floor environment as being a place where there's some really cool water rock reactions happening, but if you go too fast, then the reaction kinetics might not cut in, then it's kind of good news if you slow the flow down and let it go slower, because it gives more time for the water and the rocks to react together. The other thing that comes from that, and this is a complementary study that Donna Blackman has completed, which is in revision with G-cubed, is that this is a study of temperature flow. So within that hydrogeology, as water flows down in one place and comes out in another beneath the seafloor, instead of it actually just going horizontally, it's actually probably going to be warming and cooling. So it's going to be spiraling its way through. And that's really what these rolls show in temperature from left to right. But what's really interesting is because the flow is slowed down compared to Earth, then compared to the relatively weedy temperatures you see here for Europa and especially for Enceladus, you never exceed the temperature for life, but you do get up closer to like 80 degrees Celsius, which is a lot more close to where you might think in that 50 to 80 degrees Celsius range can be optimal for where there might be microbial habitability. And again, the reason we know that, and we can say that with certainty, is because in Earth's ocean, this is actually exactly the same temperatures. These are about 120 degrees Celsius. And this is where Jill McDermott, when she was doing her PhD with us at Woods Hole, it was these fluids from this particular chimney were the first ones, but there were many others, where we could show that you could account quantitatively for carbon dioxide being removed from the fluid that was circulating underneath the seafloor and coming back up. And you could account for it 1-to-1 with conversion into formate molecules, which was the kind of thing that Everett Schock and his colleagues have been predicting since the late 1990s. And by the mid-2000s, we'd actually shown, or the mid-2010s, we'd actually shown that that actually does happen. That's kind of what motivated us to go and look for the same kinds of things in the Arctic as well. So that's another thing you can do. If you do have a technology that can get all the way to the seafloor, then you can start thinking about what might be happening in the subsurface in terms of what the physical flow can be, what geochemical reactions might be. And again, using the same kind of white and pink notation, it can also be what's the organic circulation or what's happening to the organic molecules in these kinds of conditions, whether there's life there or not. And then secondly, if there was life there, how might you expect that to change the organic nature of or the nature of the organic matter, and would it look different if biology was involved rather than not? So you had to wait a long time for me to get started, but I've finished already. So I just want to acknowledge some funding that a lot of the tools we're using now came from our first consortium project that wrapped up about a year ago. That's where we've done doing all the physical modeling. The middle panel is the new consortium, or illustrative of the stuff we're doing in the new consortium, trying to think about specifically for Enceladus. And on the right is the fact that NASA's actually funded some of this field program to actually go out and test these technologies that we've been building. So I will stop there, and there might still be time for some questions.
That was excellent.
Fantastic. Thank you so much.
Hope it was worth the wait.
Yeah. What awesome field work you've gotten to do. That's amazing. What cool. I'm so excited to see some of these papers coming out. This is very cool. We can open it up if people want to just turn their mics on. I think they should have permission from Morgan and just voice their questions. That would be great. We can go. I think, Chris, you said you've got some flexibility until about 2 p.m. top of the hour.
Yeah. I got the rest of the hour.
I have a question.
Oh, go ahead, Brooke.
First off, that was a spectacular talk. It was perfect for this group for where we're headed. So back at the very beginning, you showed Mark Nouveau was about to do these, right? Spraying into like a cryo chamber of some sort to look at how organics change. And you mentioned they're doing amino acids. And I guess I was curious as to why not use like a complex ecosystem, like either remove cells or just use seawater in general, because we're so good, at least on Earth, tracking all of those things. Why not use, right? I understand the idea behind tracking the addition of 20 amino acids and what happens, but right, we have the technology to actually just use what seawater looks like and track it all from beginning to end.
Yeah, but that's because we only have one kind of seawater in our brains, which is Earth seawater. So something I missed out is somebody else we have working on this is also working on a 47 parameter space model for the composition of other ocean seawaters, which could be, so there the only starting point is what alteration mineral can you think of? And then they can generate these probability clouds of all the different kinds of ocean composition that might be there.
Oh my gosh.
And so we're going to try and come up with there's actually a paper that's just been submitted to Astrobiology that you guys can look out for, that one of Julie Huber's students has submitted, where Tucker had actually generated a plausible Enceladus composition. So they actually came up with a recipe of how you could make predicted fake Enceladus seawater. In fact, Erin, I think there's a preprint in bioarxiv, so I can, or Avery, if you've got it, maybe you can stick it in the chat since you're here. Because that has an Enceladus seawater recipe. And we're not saying that's the right one, but it's probably more right than using Earth seawater. So I think it's, I guess it's the experimentalist preference, Brooke, is to know what you've done. So when you end up with something different, it's trying to nail down a process rather than, if you stick goop in, this is what happens. What we are planning, Susan Lang is going to be leading a series of experiments trying to simulate what happens in the subsea floor. And in those, there very much is a plan of we do it all as an abiotic thing. And then Julie Huber's going to be working with us to choose exactly what might be a good strain of microbe to introduce and see how that changes. But, you know, it's kind of, we're trying to go like we're trying to start as simple as we can and as few parameters as we can. Because otherwise, if we just leap to, I guess we're taking the multi-generational approach of, we have time, but we're trying to inform what would actually go onto a future Enceladus Orbilander mission, let alone a drilling one. Sorry, that's a long answer for one question.
That was great.
Probably
Thanks.
other questions. Yeah.
Go ahead, Kevin.
Great talk. Question: How do we have an estimate of how long the timescales that hydrothermal vent systems can last? And I asked that because the Earth has tectonic plates, so the crust is rejuvenating. Whereas Enceladus, it's debated whether the moon is 4.5 billion years old or 100 million years old.
Yeah. So Oh, do you mean hydrothermal circulation total somewhere on Earth or an individual hydrothermal vent?
Like an individual hydrothermal event, like how are
Okay.
they very long
So
lived?
if you have something that's linked to a mid-ocean ridge, like a plate boundary, um, then they might be, if it's a single lava flow with a finite amount of heat, it might only last decades to 100 years. If it's something linked to a big crack in the seafloor, it can be tens of thousands of years. So if you think about a planet that's just cooling and thermally contracting, if you did generate some large cracks, then those kinds of things could operate for that kind of timeline. The stuff that Andy Fisher is talking about, though, is just um, imagining what would happen if you took a few miles of seawater and dumped them on our moon right now and just exploited the fact that there's topography and heterogeneity, that our moon is not a perfect sphere. And so because of that, there would be inflow and outflow places that seawater would pass through. So I think that's where the low gravity thing comes in, is that um, in that kind of setting, then the question becomes, over what timescale would you hydrate all the rocks, mineralize everything, and goo it all up so nothing could circulate anymore? So then when you slow down by orders of magnitude the rate at which the water is flowing, so that's an extra thing, right, for astrobiology. I was telling you about, if you have more time underground, then you can get warmer, so it's more conducive for life. If you're going slower, you can get more chemical reactions, so there's more chance you've actually got metabolites there. But then the third thing is, then at a planetary scale, you slow everything down, so then you get the longevity, which is also a thing you have to worry about in terms of, could life become established? So it ceases the whole thing grinding to a halt as quickly as it would on Earth because of the different gravity.
I have a question, but I also know that there are a few in the chat. If those
Oh,
want to go first, I don't know.
I hadn't been looking at the chat. Maybe someone can read those out later.
Avery, why don't you go ahead with your question and then we can
Yeah,
always
because
circle back to the chat.
Avery will know how to ask things I don't know.
Chris, I
Maybe.
think that were you showing Sentry on that in that photo? Was that Sentry or
No, that's a thing called the Nereid under ice
oh, the
vehicle.
Myriad? Okay.
So that's something I didn't say. Sorry, before you go any further.
Yes.
The little thread in that animation movie, that's actually based on the thing we use. So it's a single optical fiber about twice the thickness of a human hair. You can get 20 kilometers of thread in something about the size of a paint can. So what that means in the Arctic, what we have to do, well, it's the same problem, right? You could drill a hole in the ice and you might have somewhere of interest on the seafloor, and there's no reason why the place of interest on the seafloor should be right underneath the hole you happen to choose to drill. So you need to be able to move sideways. You don't have to just go down, but you need to have that lateral maneuverability. And you can't do that with conventional robotic vehicles because the tether that provides all the power kind of is so thick that it becomes unwieldy. You can't move around sideways. So that's kind of the beauty of that system. It allows you to send communication back. You can't power down a fiber optic cable, but for as long as your power system works, and on Earth we're not allowed to put RTGs in a robot, but if you can in a spacecraft, if you can take RTGs to space, then there's no reason why you can't have them in your little bot and have infinite power, at which point all you need to do is be able to communicate and tell things what you've done.
That actually was totally a major part of my questions. That's perfect.
Sorry.
I was gonna ask, no, that's perfect. I was gonna ask with your design, with the design of Myriad and with sort of thinking about how that would translate to a similar under ice vehicle potentially on Enceladus. I was thinking for the mission ideation, this is so important to what we're thinking about for our round 2. And so I was just wondering sort of what about that payload, and that was a big part of it, but what about that payload were you also thinking about in terms of the payload that would potentially be on Enceladus or Europa?
Yeah, I mean, I think so there are two ways to look at that. One is you could go and look at the mission concept studies that have been developed already for like Europa Lander, for example. There was a whole bunch of biologists thought about what measurements would constitute the sensors for life detection. At which point the question is, well, then we need some magical thinking to work out how to make that smaller. and fit it into the size of thing you could fit down a hole. And in fact, there was actually somebody from JPL gave a talk recently at a Network for Ocean Worlds meeting, where he was talking about the fact that he'd made a really long, thin electrocapillary device. And then he'd ended up collaborating with some people who'd been working on the EELS robot design at JPL for going down the crevasse. And they told him they had to make it more short and fat. So he had, but he'd then, he'd basically taken a long linear thing and then folded it back on itself 4 times. So yeah, I think there's both what are the sensors that you want to have and what's the form factor that will actually fit in the vehicle. And frankly, the first part of, well, what are the sensors you need is the stuff we don't have answers for right now. I would say that's really what our consortium is about right now, is for the next 5 years, is to think about, okay, what are the signatures that would come out? And so that would inform what are the sensors that you want to use.
Thanks so much. I think what we'll do, first of all, this is amazing. After we just spent a week trying to understand the very surface of everything you just said. So it's amazing. Seneca, I think I saw your hand up, and then Veronica will hit you next.
Perfect. Hi, Chris. Great talk. Thank you very much. Extremely informative. And I'm excited that we can apply some of this in session 2 for the MIF. One thing that crosses my mind in sort of bridging from the earlier studies Mark Neveu that you mentioned that Mark Neveu was doing with this is measurement of organics in terms of their dilution in an ocean relative to the limit of detection of your instrumentation. Have you found that as a challenge, particularly I'd say with some of these, maybe not organics, but like soluble ions, like really, really insoluble or really, really lightly soluble ions, like some of the irons that probably want to crash out?
No, it's kind of the other way around, really, that when we think about Enceladus, the thing, and I don't know why it was only about 2 years ago I really stumbled on this, the dissolved organic carbon concentrations or dissolved organic matter concentrations on Enceladus are likely orders of magnitude higher than they are on Earth. On Earth, just about everything is processed by life. Hardly any of it is left unchewed on. So then you get this very high mass refractory DOC stuff that nobody really knows anything about. But it turns out that hydrothermal systems, either the plumes in the water column or the subsurface, may be the only things that act on it. Otherwise, it just goes round and round the cycle. So I think that's really the issue for at the moment is worrying more about the signal to noise ratio of whatever your species is. Once we've decided what the species are we care about, is there may be so much of product X in a system that's abiotic that trying to see enough signal to know that you've definitively found stuff that must be life generated on top of that could be a real challenge, especially that what factors into that as well is we can only imagine so much geothermal gradient being available on Enceladus. So there's a limit then to even at steady state, even if it all was being used for metabolism in terms of new cell production and cell maintenance, then there's
that makes a lot of sense.
The amount of standing stock of what could be there will be limited.
Does the ability to sample affect ability of sample in terms of depth of ice relative to like thickness of ice relative to water and channels in the ice affect the ability to sort of concentrate these critical things for detection?
That's exactly right. I think being able to find hotspots, that the nice thing is that there's going to be heterogeneity, so not everything is going to be the same everywhere. So the downside to that is it matters where you go. You can't just turn up somewhere and get a perfectly good answer the first place you get to. But the converse of that is if you do have an ability to think about where you're going to go, whether it's at an interface, whether it's, and that interface, I talked about the ice-ocean interface, the ocean-seafloor interface. It could just be suspended particles. It could just be little things floating in the water column as well. They may all, any of those could provide some kind of chemical gradient. But if you get to any of those places, chances are that's going to be more productive than just collecting a bucket of seawater. And, the bucket of seawater is great for the dissolved ions and the major salts, which gives you like a planetary scale thing. But for life, it's going to be a lot easier, I think, to try and find out where the hotspots are.
Thank you very much.
Yeah.
All right, I am going to interject, folks. I do hate to put an end to this discussion because I love talking about Enceladus all day. I do want to respect Chris's time. We are just close to the top of the hour, which is when he indicated he will have to sign off. If some of the myth members, if we want to maybe stay on the call, we can check in with our Zoom host if we want to have a bit of a discussion afterwards. I would be open to staying online. But I think this is a really great opportunity for us to just say a huge thank you to Chris. This is a fantastic talk and a really great context for this group moving forward. So thank you so much for the time. Again, apologies for the technical difficulties, but thank you so much for being so flexible and making this work. It was the wait was definitely worth it.